Here's the last part. I think this is the most challenging one in terms of having little hidden details that you have to know. It's a good question. The AP exam has questions that make you think, but also use everything that you've learned. So another cell is assembled. So now we've got a fourth cell, a half cell 1, which is our old indium, that we're looking through our pane of video screen for, a half a gram, and a second cell containing hydrochloric acid with a platinum mesh electrode over which hydrogen is bubbled at 1 atmosphere. Here we've got a standard hydrogen cell. Hydrogen is critical in terms of voltages because it's considered the standard that everybody else compares themselves to. Now they've shown this diagram and they've given us the electron flow. They're really a little bit false on this because a voltmeter has got very high resistance and the electrons wouldn't be moving. You'd have to have a jumper here to allow the electrons to go through the wire. But this will show us our voltage, 0.34 volts. Now let's think about that. Based on this cell reading and the previous data, what are the standard reduction potentials for these reactions? They want to know what is the reduction potential that you would see in a table. And that standard is always compared to hydrogen. Here's why they put this hydrogen cell here. Well, hydrogen is better, I should say hydrogen ions. We've got the H plus ions here at pulling in electrons. The electrons go to the H plus and produce hydrogen gas. So this cell is producing some extra hydrogen gas as the H plus is produced. Now they're bubbling it through, but we get actually more hydrogen out than we put in because the H plus is being changed into hydrogen, and our indium is losing its electrons. It was able to rip electrons off of titanium and vanadium, but the indium plus 3 isn't capable of ripping electrons off of hydrogen. We're getting indium going into solution as indium plus 3. This plate will oxidize, and we'll see the oxidized version of indium because it's losing electrons. Now this voltage is 0.34 volts, but it's the hydrogen gaining that 0.3 volts. So this reaction that's shown here, where indium is gaining electrons, isn't going to be plus 34 volts. It's going to be negative. It's losing against hydrogen and hence the negative sign. That's the real trick for this problem. It is negative 0.34 volts. If the electrons are going the other way around, and we had a 0.34 voltage, we know that indium plus 3 was the winner, that it was great at grabbing electrons compared to hydrogen, and we have a plus 0.34 volts. But no, indium lost this, and compared to hydrogen, it lost it by 0.34 volts. Well, we've got one of these 3 points based. I'm sure a lot of students who answered this would have seen this 0.34 and said, oh, it's plus 0.34. But wait a second, that's too easy. This was the trick. So beware of easy answers. Well, what about vanadium, titanium? They're not here. Aha! But remember, the earlier part of the problem, we found out about indium versus titanium and indium versus vanadium. We found that indium was 1.29 better than titanium. So titanium is, I'm talking about vanadium. Let me get the vanadium. Here's our vanadium. It's 0.84. So our vanadium is got to be 0.84 worse than indium. Hence, negative 1.18 volts on our reduction table. We'd have to go down the reduction table to find our vanadium. And of course, titanium was our biggest loser of all. Loss of electrons. Biggest loser. Okay, chemistry humor. Negative 1.63 volts as we move down that line. That's my logic using the drawings that we made. Remember I said, draw the half cells. It'll help you. And it has. But let's go back up here. Now, I hope you understood my reasoning in terms of this. Those of you who like equations, this can be solved using the equation. I'm really a big fan of equations, but I think this is easier to solve in terms of logic. The equation for a net voltage, the voltage of a cell when you have two half cells, is the cathode minus the anode. So we have hydrogen, and we know by definition the voltage of hydrogen is 0. So we've got this half of the equation. The voltage of the cell is 0.34 volts. The voltage of the cathode, cats reduce, they gain the electrons. Cathodes always gain electrons, is 0. Anode, well, there we can use our algebra. And if you solve this, you'll get a 0.34 volts equals negative E. Hence, E at the anode is a negative 0.34 volts. We can do the same thing for our other substances. If you can use that same equation. If we remember, the voltage of the vanadium titanium was 0.45. Well, 0.45 is equal to negative 1.18 volts. The vanadium, which was the cathode, minus the negative 1.63 volts, which was the titanium. We see that this equation, using the reduction potentials that you'd find on a table for vanadium and titanium, support our previous answer, the voltage of the vanadium titanium half cell. We've solved this complex problem with probably 4 or 5 points at least on an AP exam. Logic, step by step, use the diagrams to keep you from being confused, and make sure you get plenty of sleep before you take an AP exam, because you can't have a muddled, sleepy brain solving these. Well, we've solved this problem, A, B, C, and D, and only took 3 videos.